Okay, hi everyone. Thanks for coming to our last network seminar of the term. We have Gecia Bravo-Hermsdorff, who's from multiple places, recently moved to the University of Edinburgh. Before that was at UCL, PhD at Princeton, worked at Google, lots of different great things. And she's going to talk to us about the variance and other statistics of networks. So thanks for coming, and please take it away.
Cool, thank you. So yeah, hello everyone. Super excited to be here, and yeah, thanks for inviting me. So actually, I'm going to talk about a project that I've been working for quite some time now, and I really like it, and I think it's nice for this crowd. Okay, so the topic is graph cumulants, and they are the answer for the question on my title, what's the variance and skew cathode set of a network? And so they are.
Okay. Yeah.
Okay. So they are, subgraph statistics that are very dear to my heart. Maybe because, the first one to come up with them were like me and my husband under the supervision of our dog, while we were avoiding our writing our PhD dissertation. So that was fun. But, I promise I'm not just playing favorites. So graph cumulants really are a very nice set of subgraph-based statistics that quantify the relational structure of the data. They have nice mathematical properties. They have intuitive interpretations, and they actually have already proven to be useful in practice, as I'm going to show in a very neat example, with a statistical test. Okay. So yeah, the ability to answer questions whether two networks are statistically different, whether, where does difference come from, right? So for example, if you're interested in triangles in the network, you might look at cluster coefficient, right? But then if you have a different substructure, how do you discount that? So it's really a systematic way of obtaining that. And also we can compute analytically whether with respect to a natural null model, where the difference are statistically significant. So here's the plan. We'll explain, what cumulants and graph cumulants are, why they're special, and how they are useful. Please ask questions. Actually, that's better. Yeah, and I'm going to try to go slow so you can get used to my accent and, give intuitions about things on the way. Okay, so that's actually the question that motivated this endeavor. So suppose I give you a bunch of networks, and then your goal is to assess if they come from the same distribution, comparing them in kind of a systematic way. So how might you do that? Okay, there are plenty of statistics for networks, maybe even, I don't know, too many. And then actually, it would be nice if there was a set of hierarchical statistics that you could use that would describe the network with increased amount of resolution, but still were interpretable. Okay. So the kind of things one thing you can do is look at the frequency of subgraphs, and then as you include subgraphs with an increased number of edges, then you're describing the distribution in a more in a higher resolution. But I'm going to argue that, but that's not very interpretable, right? Because, so for example, if you see that G's density is high, is it high because of lower order things, or is it high because it's actually suppose something about the network model? Okay, so indulge me a little bit. To illustrate my point, I'm going to go to an analogy with a single scalar. So suppose you are an alien, and you're studying human heights. And then, you want to describe the distribution of human heights in a meaningful way. So the first thing, with summary statistics, the first thing you might give me is the being, right? And that's the first moment and the first cumulant. Now, if you describe the distribution in terms of moments, like we have the expectation of the, the random variable two powers, you will be talking about at second order, the average square length of a human. That's not really very interpretable, right? And that's also not what people normally do, right? Like normally you would look at the variance, if you want to put it in the same unities, take the square root to get the standard deviation, or you can scale that by the mean to get the relative fluctuation. And even though there is, the same amount of information in these two statements, because there is a one-to-one correspondence between moments and cumulants, I'm gonna add these statements are more interpretable. Also, cumulants, they have like nice properties. They're just a better base to look at your random variable. Right. And so the type of statement in the top, it's what it's looking at subgraph densities or like motif analysis. Subgraph densities are really the moments for network, as I'm going to explain. Well, what I'm presenting now is the analysis of this statement. Okay. Okay, so we're talking about, the first two cumulants, the mean, so that's like the center of mass of the distribution. The variance, it's the spread around it. After that, you have the skew, that it's like the asymmetry on this spread, and then after that you have the katose, which is like this asymmetry due to large deviations or small deviations, like how fat the tail is. And actually the hierarchy continues, right? You have one moment and one cumulant for each integer. And here I just put in the formula, like the kappas are the cumulants, and then the things in the brackets are the moments. So for example, the variance, it's the second moment minus the first moment squared. And and the mean is both the first moment and the first cumulant. So yes, moments and cumulants are polynomials on each other, right? Okay. So, yeah. And if you have multivariate random variables, then you're going to have more cumulants more moments and cumulants at each order. So say we have heights and weights of dogs, for example. At first order you have the mean of each mean. At second order, for the moments, you have the expectation of x squared and the expectation of y squared. But then you also have like the product of the two. And then you have the correspondence, the corresponding cumulants. So variance of x, variance of y, and covariance of x and y. And continuous, at third order, you look at the different moments you can have with different ways you can product three things. Okay. So now if our random variable is a graph, then the cumulants are in the moments and the cumulants are indexed by subgraphs. So for the moments, these are like the subgraph densities. And that's because the data is in the edge, so that makes sense. So let me explain exactly what a graph moment for a network could be. So say you have like your big network here, and you want to compute the graph moment associated with this subgraph. So I'm calling graph moments and subgraph density the same thing. Okay, so I want you to think about this subgraph as a sort of stencil, and then you can randomly map the nodes of this subgraph into different nodes of your network. Okay, that's the injector here. And then now we're going to count what the good maps. And so if all the edges are there, then that's a count of 1. If none of the edges are there, if any of the edges are missing, that's a count of 0. And it really doesn't matter what happens outside the stencil. That's the homomorphism part as opposed to induce, right? Okay, and then the density part is that you take the expectation of discounts, average over all injective node maps. So if a big network has like big n number of nodes, that's polyfactorial of G1 has zero n, the number of nodes on G1. Okay, and that gives you the probability of if you sample 1 nodes in your big network, what's the probability that you're going to see the subgraph? Okay. Okay, so just repeating the definition, injective homomorphism density. Okay, any questions about? Yes.
Just to clarify, when you say expectation, you're not actually thinking of a probabilistic model, right? Is it the empirical distribution that you're looking at?
Yeah, on this one, yeah, I told you how to compute the empirical one, yes. And yeah, I'm going to talk about the probabilistic model like soon, but yeah. Okay. Any other question?
Yes, what was the difference between when you chose it to be a tick in a class?
Oh, yeah.
Sure. If
Sorry.
you go back.
Yeah, sure. Sorry. Yeah, so I think it's just like once you like you look at the stencil, and then if all the edges implied by it are there, that's a tick. That's a good count. If any of them are, oh sorry. If any of them are missing, then that's 0. That's 0. Okay.
Sorry, can you still explain maybe then what do you mean by the density? Is the expectation also the tendency there?
Yeah, sure. The density I meant like the expectation over all the node maps. So that's why I said like, so how many ways can you map the nodes of your time subgraph into different nodes of your big network?
So density not in the probabilistic sense, but density in the sense of density.
Yeah, averaging over all maps.
Okay, cool.
And little n is the number of nodes in the subgraph?
Yeah, so big N would be the number of nodes in your large network, and little n the number of nodes on your subgraph that you are applying with the corresponding moment. Okay. Right. Okay, cool. Okay, so I put it here the form for the third cumulant of a scalar random variable, and I told you now for moments and cumulants, we're just going to have subgraphs instead. So, anyone wants to guess what we're going to have for the cumulant of the triangle? What is this term going to be? It's easy. It's exactly what you think, probably.
That's good.
Yeah, exactly. So that's just, that's just the density of triangle. And that's because like on these expressions, that's always like this. The first term is the corresponding moment. Anyone want to guess the rest? Like what might it be? Like because
Is it like the sub of the triangle?
Yeah. Okay. Nice, right? Like that makes sense. That's like that makes sense that would correspond to G1. And here is like so the edge on itself is just the edge density. So you'd have the edge density cubed. Right. And here, like for G1, anyone want to guess? It's kind of, it's actually the same thing. So okay. But what about for G1? What would we put here? Right, that's a bit less clear. Okay, and as a matter of fact, right, like how did we get these expressions in the first place? And which is alternating sum of minus and plus. Okay, so let's go back to the definition of classical cumulants. You may have heard it in terms of like the coefficients on the log of the moment generating function, but actually there is an equivalent combinatorial definition that's much nicer, and it's also like the thing that you use to generalize to other things. So I'm gonna give an example, but essentially, like for a moment of a given order, you are gonna consider all partitions of R elements, and then you sum over the partitions, and you product within the block, and that's the corresponding cumulant. So partition, right? Like you have your set of stuff, and then you divide it on disjoint blocks, and together they make the set. Okay, so let's get an example. So how many ways can we partition, one thing? Just a single way, right? Like the thing by itself. How many ways can we partition two things? So there is a partition where the two are in the same block, and a partition where they are in different blocks. Okay, just one more. What about partitioning three things? Again, the partition where the three things are in the same block, the partition where the three things are in different blocks, and then for the partition where you have two things in one block and one thing in the other block, we have three different ones, right? Okay. Okay, so, and now we just apply the formula. So for the first one, that corresponds to the beam, which is the first moment and also the first cumulant. For the second one, now we have, the second moment equals variance plus mean squared. And you can see that like you can invert this formula, right? So you can, I'm giving moments as a function of cumulants, but really like you can just invert it. This is just like the nicer direction. Okay, so does this make sense? And yeah, just a comment. And this is actually cool, right? That you can see, like, if you're talking about a multivariate variable, then like that's what you would get the covariance by just, instead of saying that they are the same, the two things here, like thinking about it as x and y. Anyhow, okay. So how are you gonna do that for graphs? So it's essentially almost the same thing, but now we consider partitions of the edges of the subgraph. And the partition has to respect the graph construction. So for the partition with three edges on the same block, we have the cumulant associated with the triangle. Not triangle, sorry, like the three line. Let's see. Anyhow. Okay, and then we have the partition where the three edges are in different places that correspond to the edge density cube. And then for the partition where you have two edges in one block and one in the other, there is kind of like two ways where they share a node and one way where they don't. Right, so it's essentially like almost the same thing, but now respecting the graph structure. And yeah, and again, I can, so then like the conversion from, these moments or bare subgraph densities to graph cumulants kind of introduce terms that cancel out the part attributed to smaller subgraphs. Like intuitively, you can think about it as, the graph cumulant for a subgraph little g as capturing something. Yes, sorry.
I'm just wondering, so for the second to last one, the the edge, how do you actually count them? So suppose I've got three isolated edges. Would that be a count of 3 factorial? Or
yeah, I'm counting them by put them on blocks. So like I'm considering all partitions of this set of edges. So
just thinking in the empirical distribution. If you've got 3 parallel lines, what would that translate to in the cumulative AII? Okay.
Oh, I see what you're saying. Yeah, so if you wanted to do that for three disjoint lines, so this is the cumulant of the distribution, by the way, because then you have, then you would, again, actually consider all the partitions. They would just be like, in one partition, the three disjoint lines are the same thing. And in another partition, the three disjoint lines are separate, and you would get the edge density Q. No? Like, I guess, so once you estimate the things for disjoint, then a lot of things cancel out, but conceptually the formula is the same. So like, so you're saying like, so is it okay?
Yeah.
Okay, the texture was weird. I'm like, oh. Okay, so you have these years of graph, three disjoint things. Then let's just look at these partitions here. So like you can think about them as
I'm just thinking about sort of the K dash dash, K slash dash, so K line. So the second to last term,
this one.
that one exactly. How would I think of it?
Yeah, this one is because I said the partitions have to respect structure. So you see that in there's two ways that the things share an edge. And then here, so if I partition with these ones, they don't share an edge. And then this corresponds indeed of the subgraph that is two disjoint edges. Like so it corresponds to G subgraph. This one.
Would you count the second last term in the three isolated edges graph?
Mhm.
You count that 3 choose 2 times. Right? When you estimate the empirical.
We're gonna go over how to estimate the empirical one and like normalize it properly. But because indeed it's different the formula for the distribution than the formula like we know that, right? Like variance, we have the n-1 to unbiased, right? With these things we have a way to unbiased too. It's just a bit more clunky, but actually it's not that. Sorry. Okay. Okay, makes sense? So, I just repeated the formula. Like, so just we see the analogies, like in one case, partition of a set of our things, now partition of the edges. Okay, so we're talking about distributions, right? Like what graph distribution are we gonna look at? So let's focus for now on undirected graphs. I mean, with graphs, like if you plot them, it doesn't really make sense, right? I mean, it's hard to visualize. So one thing you could do is like look at the adjacency matrix, and then here you can color it like by put zeros in white and ones in black, and it's symmetric. And here I have like an Arrow-Schrödinger graph. So I had 32 nodes, and then I flipped a coin independently for to give them an edge. And okay, that's how it looks. And then here I have 32 more. It's starting to looks like it's converging, right? And actually, it does. It converts to a gray square. So like this is what's called a graph form. This one is very simple. And that's kind of like the limit distribution for dense graphs. So you can think about it as like an infinite graph. That's the so okay, I was gonna give one more example, but first let me define what it is. So a graph one is a bounded symmetric, on our case, measurable function over the unit square to the unit interval. And then like the way you sample from it is first you sample latent positions for the nodes uniformly. And then given these latent positions, you include an edge with that probability independently. So that's what a graphon is. And like the latent node positions here, like one example would be the more familiar for stochastic block model, right? So, but you know, you have two communities that are more connected to each other than outside of each other. And I just did the sampling on the other direction. But you can have like more weird things, more like fractal things and stuff. And yeah, there is this, I mean, there is a sense where G is really the limit distribution for dense graphs. So for example, for every subgraph density, it converges. Any questions? Okay, so why did I talk about G's, right? It's because another property of cumulants is that for not like for distributions that we know and like the Gaussian, they are better described with cumulants. So for example, the first, like for the Gaussian, just the first and second cumulants are non-zero. And like the same thing happens if we look at the graph cumulants. So first, like, you know, the simplest random model you can have, so just an average range. Here I'm just computing the moments and the cumulants of the distribution. So yeah, the moments is really easy, right? It's just gonna be the probability to the power of number of edges in the subgraph, given that the thing is independent, right? And then like the cool thing is that for the cumulants, just the edge density is non-zero. All the other ones are zero, indicating really that there is no other information besides the edge density. And so here I've made a symmetric change in the degree distribution, and then like the only thing that changes really is the stars, which are associated to the degree distribution. Oh, by the way, I scaled both of those by the density, in the error range, just so we could visualize better and maybe give the moments a chance to distinguish more. I guess my point is like, everything here is kind of the same. I just change the probabilities and only the star cumulants are non-zero.
Why are these the only cumulants you need to show?
I need to show, you mean like why I'm not showing more?
Yeah.
Yeah, because I'm cherry pick the ones that are interesting. Like just to make a point of like kind of just not cherry pick, like because here like really all the other ones are zero besides the stars. And the stars, if you think about it, they're associated with the degree distribution, right? Like how the nodes are connected. And that's like, because this is kind of the same thing. It's very symmetric. I just changed, like now you have one community that has more like probability of connecting and one that has less, but all the rest is symmetric. And yeah, the point of these pictures is just to show that like there is, when representing a distribution in terms of the cumulants, they kind of look nice, let's say. Okay. So here, the simplest model for clustering, right? So you have two communities that have the same probability. And then here I'm connecting, within the same community with a higher probability, 0.75. And here between community with less probability. And what you can see is that here the only cumulants that are non-zero are the simple cycles. And it makes sense because like, on this, it's a very simple model. On this, it's like, okay, so if I'm connected to something, then there is more chance that that thing is connected to the other thing. But important thing is like, given that, for example, given that the density of the things are the same, the cumulants for the stars are zero. And now here, so if I just inverted it, so yes.
So this is now not the empirical distribution. These are the theoretical cumulants under the Grafman model that you introduced.
Yes. Because okay, yeah, we're gonna go over this. Like for the Grafman model, it really doesn't make a difference if it's like injective or not the moment. But yeah, so here I'm just computing like using the form, like integrating over the thing. That makes sense. Right. Okay, so yeah, okay, so the nice one about this one, so I just changed the probabilities of the communities and between communities. I just flipped it. And so it's like more bipartiteness. And what you can see is that like now the cycles with even number of edges have the same but negative cumulant. That makes sense, right? Like, because for example, in a triangle, you don't have, sorry, in a bipartite graph, you don't have triangles.
Does this depend on the particular values that you chose?
No, this is true. So,
But to the diagonal and triangle to be the same.
yeah, this is a symmetric one. So that yes, both communities have the same probability. So they have like the same density.
Otherwise, it's
Yeah, I'd rather only get this. So, right, I only get this because it's this particular model where like the two communities really have the same density, and the only thing that changes is like in or out.
It's important that the communities occupy the same amount of space in the graph model here as well.
For only these ones to be positive, yes, because if I had, for example, that one was more probable than the other, then you would see some difference on the degree distribution. Please.
Do you have intuition as to what would happen if one of the communities was larger than the other? Do these the triangle, the square, and the rings basically, do they still remain the same sign but reduce in magnitude, or what happens if I have one larger than this one?
Yeah. Okay. So if you had, actually, I have an example. But so if you had more one that would be more like frequent than the other, then it would be other cumulants would be non-zero too, right? Because you're deviating more from the baseline of Ehrlich-Schreini. And then, so let's just look at this example that I made here. So now I'm like having a correlation between clustering and degree. And like, okay, so I want to point out for this graph in particular here, okay? And then like, just watch what happens if I switch it. Now it's negative. So this particular subgraph that's like, kind of a correlation between clusteriness and the degree is indicating like its sign kind of like capture that. Makes sense? No?
So I'm still sort of
Yeah, sorry, okay. So I mean the other okay, so the more you make your distribution more complicated or deviating for Ehrlich-Schreini, then you start having cumulants also that are going to be non-zero. And then they have other interpretations. And also if you start looking at like, it's not perfect, right? Like it's not that everything is going to have like a nice word interpretation actually. But here I'm focusing on one thing that, because the thing is like, if you take the complement, you just flip the sign of the odd cumulants, like we can use this one, like this one is kind of like detecting this correlation between clustering and degree. Oh. Okay, so, but these were just, this is more like just to get a flavor of how distributions look on that. I'm gonna show an application that I think it's gonna be like nicer. And just this was, it doesn't matter. This was just to like I took a random thing, more or less, just to illustrate the point that if you take the complement, then the odd cumulus change sign. But okay, so it's to get these expressions for the cumulants, we have automated the formulas, and we can do that not only for simple graphs but also for directed graphs, like graphs with weight. So in this case, you like the correct thing to do is kind of like multiply the weights, and graphs with node label. I had some example here, but it's a bit of just don't apply to data. Okay, so let me show how the graph cumulants are useful in practice. Okay, so I'm going to compare the graph cumulants with the corresponding graph moments, like as fair as possible. I mean, super fair. And the point is that, like, really very conclusive, the graph cumulants do better. And so the application is very simple. It's just a two-sample hypothesis test where your samples are actually collections of graphs. Okay? So you have two graph distributions, GA and GB. You can think about it, I don't know, like a machine. And then you press a button from machine A, you get a graph. Machine B, you get the other. Okay, and your job is to tell whether these, secretly, these distributions are the same. How they relate to each other. So, okay, so one thing, for example, like if the graphs coming from A have many more edges than the graph coming from B, then it's a very easy to distinguish thing. So I made sure that all the distributions had this, same edge density, so that both tests could rely on like, how the edges relate to each other. And okay, so the two statistical tests are essentially the same, meaning that they have the same structure, the same assumptions, and the same computational complexity. The only difference is that in one case, we're going to use the subgraph densities of the sample as the estimation of those of the graph distribution. And in the other case, this like the cumulants. Okay? And here's how the test works. So first, you choose the subgraphs that we're going to consider for the statistics. So in our paper, we took subgraphs, connected subgraphs with at most R edges. And then for each sample of S graphs, you estimate the graph moments and the graph cumulants. I'm going to explain these, and then after explain how we do the estimation part. So like just the structure of the test. So yeah. And then like, okay, so then to compare the distributions, we need a notion of distance. And what we use is the Mahalanobis distance square. So think about it as kind of like a generalized z-score. So the way you compute it is, you take the expected covariance matrix of the inferred statistics. So actually we do, for the test, we use subgraphs with up to R edges, but then to compute the covariance, we need subgraphs with 2R edges. Because we compute the covariance analytically. Okay, then you sum the covariance of each of the samples, and then you take the inverse, and then you quadratic form it with the difference between the means of the statistics. And you do it either on the space of unbiased graph cumulants or in the space of moments. So this is the general right. This is the general form of the test. Does it make sense? Okay, so then we generate a bunch of synthetic data using different SBMs, but not two different ones. And so yeah, okay. So then we compute the Mahalanobis distance square between the pairs of samples, and then we classify as coming from the same distribution or not, right? Yes.
How do you take the randomness into account when you classify whether or not it's the same distribution?
Sorry.
So when you classify whether it's not the same distribution, how do you do that?
I'm gonna just use the AUC after to summarize the curve. I'm just plotting here, like, you could choose a threshold and then just say after each threshold is in one or the other, right?
In statistics, we often use confidence intervals. We have
so
then you have confidence intervals, and you say because it might just be that the cumulative confidence intervals are wider than the one for the moment.
Yeah, sure. Like okay, we're gonna do that empirically first, but then I'm gonna show that the cumulants follow a chi-square distribution like very tight under the null hypothesis, even for small graphs and small number of samples. But here I'm just showing I'm just plotting the computed things, and then like right. So so yeah, so this is the square, like the square Mahalanobis distance squared that we use to get to the threshold for same or different. And then like that's going to induce, right, like a rate of false positives, incorrectly concluding that they were different, and then a rate of true positives. And here, like, everything is summarized in the ROC curve. And one thing you can do is just summarize this curve with the area under the curve. So a value of 1 means a perfect test. A value of 0.5 means a test that's random. And right. Oh yeah.
Sorry, I just didn't understand the actual decision. So you get distances for both of these. So then, how do you make what is the actual classification?
Yeah, sure. Okay. So I get so here's the Mahalanobis distance square. Is the thing like the GIF that we're gonna use to threshold. And I mean, different thresholds would induce different false positives and true positives rates, right? So there are better ways to you could pick. There are better ways to pick where to do, but let's do just something dumb first, and just take the area under the curve as the thing, as to summarize, to summarize this, and that's this plot. And
what's your kind of ground truth here that you're comparing to? What decides a false positive from a true positive? Yeah.
Well, okay, sure, because I'm simulating this data, right? So I know whether the thing came from the same distribution or not. Yeah, so this is simulated data. So I right, okay, right. So then I know and then I compute the things between and within the distributions.
I'm still not understanding. So you get two distances, right? One for the cumulant, one for the.
So you have.
But then, okay, so then I need to say I have a distance, right, and I want to say I'm gonna predict this is or is not from the same distribution. Like how is that decision getting made? That's the thing I'm not quite.
Like this distance between the pairs of samples, right? The Mahalanobis distance, right? So I have, and then I have the case where it was from the same sample, like from the same distribution versus not, right?
Yeah.
So yeah, I guess I didn't articulate it. Like, sorry, yeah. So
So I get you have a score, right? You get a score.
yes.
But then like how do you say this is I'm classifying this as same or different distribution? Like how does that decision actually get made? Is it a
like by
threshold?
thresholding the Mahalanobis distance.
Okay.
So you can threshold that it. So that's what this plot is saying. Like you could threshold it at different places, and like at different places that you threshold, then you would get a different false positive rate and a different true positive rate. So it's a choice of threshold.
Okay.
Because
so that's what this ROC actually is different thresholds.
Yeah, exactly. Yeah, sorry that I didn't explain it well. Yeah, so the ROC is just summarizing what would happen. So, like, if I were to choose different thresholds, right? But this is a simulation, a single simulation, right? If you're going to do a simulation study, you do want to vary the parameters, and so like for each thing, so and the way that I'm summarizing the result of the ROC here is via the area under the curve.
How is your simulation set up? So do you have the same number of true positives? So,
Yeah.
and do you use the same alternative distribution for the same technique graph on distribution all the time?
No, I didn't. Okay, so for this, yeah, like okay, so right. So here is a particular choice, right? Because it's just a given particular simulation of SBM. But we test like different SBMs. And we also did some simulation on semi-synthetic, like on real world data that we graphonified. So yeah, like actually, if you want to, yeah, like it's just as simple as, I mean, for this one, it was just a simple SBM that we were like comparing, but there was not too different, so that at least we could see the tests like doing something. Oops. Okay, I'm running out of time. Okay. Okay, so here I'm here is summarizing the result of a bunch of simulations. So for graphs with 256 nodes or 128, and like the point here is that in general, like graph cumulants do better, and that's true like for other settings too. And also, like if you estimate using the cumulants, you can compare single graphs. And I am running a bit low on time, so I'm gonna go a little bit fast so we can talk about how you might estimate these things. So yeah, just this is like we did semi-synthetic data, so like we took gene interaction networks and compared them. We made sure like that they had this, like the same edge density and stuff. And here is just like saying, I mean, yeah, if you we made sure that the edge density is the same. So if you want to use the edge, you cannot distinguish between them. Okay. So one question is like, why the graph cumulants do better? And that's because the fluctuations on graph cumulant space, they look more Gaussian. So like for both tests under the null hypothesis, if you had like very big number of nodes or like very big number of samples, then both of them would follow like under the null hypothesis, they would follow a chi-square distribution, like both moments and cumulants. But the point is that like the cumulants, they follow a chi-squared, like even with I think this is like 128 nodes. Even with a small sample size and graph size. Even right, this is not like this is simulated data. It's not like like that's a perfect price spread. And like and I mean, if you follow a non distribution under the null hypothesis, then you can control the false positive rate, right, by choosing an appropriate threshold. So that's very convenient. That okay, so let me do the review. Okay, so I said like how we estimate these things, right? Because I was talking about distribution. So one thing is that for single graph ones, the moments of the disjoint graph, like if you have two subgraphs that are disjoint, the moment just products. And for the cumulants, if the subgraphs are disjoint, then the cumulant is 0, which reflects the independent structure of the edges and can be used too. So one thing is like there is a difference between injective homomorphism and just the homomorphism. So the injective homomorphism that I explained on how to estimate in the beginning, this is the thing that's the unbiased estimator for the distribution moments. And that's the thing that gets preserved under node subsample on the graphon model. But the thing that product is just the home, like not necessarily injective. Okay. So this is supposed to be like kind of like okay, I'm showing kind of like a scheme of the pipeline, right? Of things that we can convert. These quantities of subgraphs, they relate to each other in so for example, if you have a fixed number of nodes and you have the homomorphism counts, then you get the injective counts also, right? And the nice thing is like the homomorphism counts you can get easier with fast matrix multiplication. Then you can convert that to the injective ones. And this is the thing that you use to estimate the moments, as I was saying. And then this gives also the estimator. We use that for estimating the cumulants. And that's because, let me show you. By using this property, distributionally, the unbiased estimator of the cumulants, adjust, you substitute the edge density square with just for example, the edge density cube with just this, with the disjoints, because of this assumption that the things are coming from a single graphon. Yeah, so like you can convert between these things and then get the estimators. So, for example, the covariance between the two graph moments, so the first term is going to involve a product of moments on the finite graph, right? So on the finite graph, the injectives are not going to product. So you need to do a modification of the disjoint union, you get discounts, and then you convert back. So all the time you're using the algebra of subgraph statistics to convert between these things in a convenient way. I'm gonna maybe, yeah, I'm gonna because I'm gonna skip that. But so another thing that about cumulants is that cumulants of so if you have two if you have variables that are independent, the moments product, and right and the cumulants when you add, they add. And that's true for ours too, on a notion of addition. But and that's the proof. But I'm gonna skip, but we can talk about it more. I'm just doing addition in the like entry-wise of the adjacency matrix. So, okay, in the big picture, like, you know, is that we got these like nice principled intuitive sets of subgraph statistics. And like, I mean, you could ask like, and then, right, like where are you gonna use these? Like you have big deep networks that are like, you know, doing things like, is intelligent feature engineering still useful? And like, I'm gonna argue that yes, because I think like lots of the back like progressive machine learning comes from intelligent choices of like, for example, convolution neural networks for vision, like intelligent priors and transformers for large language models. And like a bit like the edge and orientation detection cell in the first layers of our visual processing, the graphical ones, they kind of give this principle first layer of contrastive features when looking at the relationship between edges in the network. And I mean, the idea is quite general, well, cumulants is one example of a mobile, like the relationship between moments and cumulants is like one example of Mobis transforming a poset, and like you have other ones. Wait, I mean, in terms of future direction, I think like yeah, these relationships could be used like thinking about other posets for subgraphs and using that and like think another application is mathematical AI. So there is this like nice 6-graph fit program that they generate like conjectures over graphs, but they think about the graphs like kind of pointwise. But really here you have like and is this algebra, you have like functions over it. So I think trying to incorporate that would be a nice feature. Another thing is like all these things rely on counting subgraphs of medium size. So thinking about how to do for certain families, like to count it more efficiently, I think it's a nice avenue. And also like if you count homomorphisms, like not necessarily injective, it's easier to count, and then you can pass to the injective ones. Yeah, and like, you know, more applications, and yeah. Okay, that's.
Great, thank you very much. Are there any more questions? Yeah.
Yeah, thank you very much for interesting talk. So in the area of probability, I think this object has been well understood as a paper by Kauer and Berlin, which looks at, don't call it cumulants, but they look at centered counts which are centered in a way that you get the cumulants that you get, I think. And they give a multivariate central limit theorem.
What you're saying for that for moments, you're saying for graphs?
For graph functionals, especially accumulants, the ones that you're looking at, so they take away the mean for every indicator, which is, I think, what this relates to.
Yeah. So the centered moments are actually like, well, for the
No, it's not the moment.
No.
I think you can have a look at that paper.
Okay. Oh, cool.
It is exactly so for each indicator variable, you take away the mean, and then if you multiply that out, you get exactly the cumulants. So you can try it out. So they have a normal approximation, but there are two issues. One is that, for example, quite often the covariance matrix is not properly invertible. So we know in the limit it will be degenerate. So there's a problem. The second one is a model specification. It behaves very well when you've got the right model, but as soon as the model is slightly wrong, it's completely off. So I wonder whether you run into the same problems.
Okay, so yeah, I ran out of time and I didn't do okay, but so you can see here that we do manage to compare single graphs, right? Where the moments you can't, and that's because we are using like we can do use the unbiased estimator. We can use this relationship that the cumulants of disconnected things are zero to actually be able to have an estimator even for single graphs.
But you can also compare single graph, but you just have to calculate the covariance between
So we are computing.
for the clouds. It's not so hard.
We are computing the covariance analytic. Are you saying like for the moments like?
But if you have the empirical moments or empirical time, you can also look at the covariance matrices.
Yeah, but it's not going to be if you have a single one. So I think I have a slide of that.
Well, the cumulants at the moment they are 1-to-1. So
Right.
so you can get the cumulants from the moments and the other way around.
Right, but in terms of estimator, they lead to different estimators on the distribution, right? So for example, if you want, say you have a normal, like just a normal distribution, and you want to like it's different the estimator you get if you're trying to estimate like the second moment x squared versus if we are matching the variance.
Yeah, of course.
Right. So the same thing. And what does it do to measure the cumulant instead? It kind of you have an estimator that allows for more spread, and so I guess like in terms of estimators, the cumulants give better ones with lower variance.
Yeah, I mean, I think that is true if you've got the correct model, and if you try it under model specification, you might find that it gives a lot worse than models. So this is what how I really. So I would be surprised if you didn't.
Okay.
Any more questions? If not, let's thank you again. And thank everyone online. And yeah, we'll see you next year. The seminar. Bye.